So our first application is a block which is sliding on an inclined plane. So here we have an inclined plane and here we have a block of mass m. So this is our block of mass m, and this inclined plane is making angle theta with the ground. Okay. So let's find what are the forces which are acting here on this block. The first force which is acting on this block is the weight of this block, which is downward, and as we can see, this direction is parallel to this vertical direction of the plane. So this will be mg, the weight of the block. And another force which is acting between the surface of this inclined plane and the block is frictional force, which is pointing in this direction. This will be our frictional force F, okay, denoted by small f. And the reaction force from the surface of this inclined plane will be perpendicular to this plane. So let's draw a perpendicular from this plane, inclined plane, that will be pointing in this direction. This perpendicular is called as normal reaction. This is making 90 degree with the surface of the inclined plane, and let's denote it with N. Now let's write the components of the forces. We know that the total force acting on any system can be expressed as Fx I cap plus Fy j cap plus Fz k cap, where Fx I cap is the total force acting along x-axis, Fy is the total force acting along y-axis, Fz is the total force acting along z-axis. We can see here that this is the whole system is inside a two-dimensional plane, so the force component along z-axis will be 0. So Fz will be 0, which directly implies that mass times acceleration, which we can also write it as m times z double dot, that will be equals to 0, which means the acceleration along z-axis is 0, and simply the velocity is also 0 along z-axis. Let's now move towards our x and y component. So along y-axis, let's see what are the forces acting along y-axis. One of the force which is acting along y-axis is our normal reaction. But we know that the mass is sliding down along x-axis. So let's assume that this is our x-axis, and let's say this is our y-axis for this inclined plane. And if we can see that the mass is traveling along x-axis, so hence the resultant force is along x-axis only. The net force along y-axis is 0. So let's write here our F of y, the motion along y direction. So we know that there is no motion, along y direction, along y direction. Hence this implies, y double dot is 0, the net force is 0, or we can say, which implies F of y, the net force acting along y-axis is 0, and we know that the net force acting along y-axis is N and one of the component of mg. So we can split this component of mg into two components. One of them is here mg cos theta, and another one along this side, along x-axis, that is mg sin theta. Keeping this angle as angle theta. So this is mg cos theta downward. So we can say that Fy is nothing but N is pointing upward and mg cos theta is pointing downward. Hence it is minus mg cos theta. Since the total force acting along y-axis is 0, so we can say Fy equal to N minus mg cos theta, that is equals to 0, or which implies N is equals to mg cos theta. This is our equation number 1. Now let's figure out our net forces along x-axis. So let me scroll on the other side a little, and let's write our equation for net force acting along x-axis. So the total force, because the particle is moving in downward direction, so that downward direction we have assumed it as x-axis. So the total force along x-axis or along x direction will be, let's say, f of x, and that f of x is nothing but, we have one component mg sine theta that is pointing towards x-axis, and frictional force is pointing in the opposite direction, so mg sine theta minus small f. This small f denotes the frictional force. Now this resultant is non-zero. So if the system is having some force, by Newton's law we know that if any system is acted upon by any force, then there will be some mass times acceleration along that particular direction. So m times ax denotes our acceleration, and that will be denoted as mg sine theta, and frictional force we know that is equals to mu times normal reaction, mu times n. From equation 1 we know that normal reaction is nothing but mg cos theta. So let's substitute that in this equation. So this will be mu times mg cos angle theta. Let's cancel out all the m's. Let's divide the whole equation with m. We left with acceleration of the particle along x-axis, that will be equals to g sine theta minus mu g cos of angle theta. This is the acceleration along the given direction. We can also rewrite this acceleration as double derivative of position d square x by dt square, and that is equals to g sine theta minus mu g cos of angle theta, where double derivative d square x by dt square on integration will give us the velocity, because we know from our earlier elementary classes that integration of a dt is nothing but the velocity of the particle. So let's integrate this equation on both the sides. On integrating on left side and right hand side with respect to dt, let's see what we get. Let's keep a bracket here and dt. So integration of double derivative a dt is nothing but velocity, right? So we will get here velocity, which is dx by dt. Let me repeat again. Integration of acceleration with respect to time gives us velocity, and that velocity is the single derivative of position, which is dx by dt. We can also write it as v. Okay, so let me write it here as v, and that will be equals to integration of this. We can see here in this bracket there is no component of time, so integration of this will be g sine theta minus mu g cos theta. Integration of dt is t plus the integration constant. So if you put the initial conditions, assuming the initial conditions to be at t equal to 0, velocity of the particle was 0. We know that initially when the experiment started, there was no velocity of this object, so velocity was 0 at t equal to 0. Let's substitute here this situation. We will get here on the left hand side of this equation, let's put it in a bracket. So this equation, on putting here LHS and RHS for v equal to 0 and t equal to 0 condition, we will get here 0 equals to 0 plus c1, and that implies c1, the constant, is 0. So we got our velocity of the particle, which is falling down on an inclined plane, to be v is equals to g sine theta minus mu g cos theta whole into t. We can also find the position of the mass or the block at any instant. At any given instant, what will be the position of the particle when it is falling down or sliding down that we can find by integrating this whole equation once again with respect to time, because we have learnt earlier that integration of velocity with respect to time gives us position. So integration of v dt will be equals to, on the right hand side, integration of g sine theta minus mu g cos theta t dt. Now this time we have a t on the right hand side. So left hand side we will get simply integration of v dt is position x. On the right hand side we can take g sine theta minus mu g cos theta. So g sine theta minus mu g cos theta, common out, integration of t dt. And integration of t dt is nothing but t square by 2. So I hope you know this. Integration of t dt by using the first formula, the basic formula of calculus, that is integration of x to the power n dx is nothing but x to the power n plus 1 upon n plus 1. So we can get here t to the power 1 plus 1 upon 1 plus 1, we get this, and plus an arbitrary constant c2, and putting the initial conditions again we will get that constant as 0. So this is the position of the particle at any given instant, where t is the time, that instant at which we want to find the position of the particle while it is in motion through an inclined plane. I hope this is clear to